A team at Max Planck, Ellis Tübingen, and ETH Zurich trained language models on a corpus filtered down to the American elementary school curriculum, and nothing above it. The point wasn't to build a small model, it was to find out whether anything you do after pre-training can push a model past what its data ever showed it. Here it is, straight from the source. Here's the measurement problem this attacks. Modern models are trained on essentially everything, so when a new technique makes one better at some task, you can't tell which thing happened. Did the model acquire a capability, or was the capability already latent in there, and your technique just elicited it? With an unknown training set, there's no way to separate those. So this group made the boundary known on purpose. The dataset is called Little Curriculum, 88 billion tokens distilled from FineWeb EDU through a 5-stage filtering pipeline, aligned with the Common Core standards for kindergarten through 5th grade. Concepts, facts, and vocabulary taught above grade 5 are explicitly excluded. That exclusion is the whole instrument. It puts a known ceiling on what the model could possibly have seen. The design is a clean A/B. Filter the corpus, then pre-train from scratch at 3 sizes: 600 million, 1.3 billion, and 5 billion parameters. Every one of those gets a matched control, trained on unfiltered data, with the same architecture, the same token count, and the same recipe. Only the corpus differs. Then you test inside the curriculum and outside it, and the gap is attributable to the data and nothing else. One thing worth doing yourself is checking how much data this actually is per model. The corpus is fixed at 88 billion tokens, while the models range from 600 million up to 5 billion parameters, so the tokens per parameter ratio moves a lot across the sweep. That ratio is just corpus size divided by parameter count. Let it run. The smallest model sees about 147 tokens for every parameter it has. The 5 billion model sees under 18. So this isn't a starved run at the small end. The constraint being tested is what's in the data, not how much of it there is. The big model is the one on the tighter data budget, which matters when you read the scaling result next. Then they threw the standard toolkit at it. Scaling model size improves performance within the exposed curriculum and extends modestly to problems on the same learning trajectory, but does little on problems needing more advanced capability. Post-training with GRPO significantly boosts in-scope ability and still fails to recover the beyond grade 5 gap, even when the post-training data itself is out of scope. In-context learning, with the prompts they tested, unlocks no new out-of-scope reasoning either. The author's summary of it is the phrase elicitation, not acquisition. Every intervention amplified what the curriculum had already taught, and none meaningfully improved out-of-scope performance. In this setup, the pre-training data set the effective capability ceiling, and the things we normally reach for afterwards move the model within that ceiling rather than past it. 2 honest caveats before you take this anywhere. It is one curriculum, one filtering design, and the evaluations they chose. And the authors hedged their findings with "in our experiments" rather than stating a law. And it is not a claim that large frontier models cannot generalize. It's a claim about what these interventions did against a known data boundary. What makes it useful is that the boundary was known at all. So, 88 billion tokens filtered to a 5th grade ceiling. Models trained from scratch at 3 scales, each against a matched unfiltered control. Scaling, post-training, and in-context learning, all amplified what the curriculum taught, and none of them broke past it. The models and the corpus are published, so the boundary is there to test against. That's the real contribution. Now you're one step ahead. Subscribe to BirenAI to stay there.